In this video, we are going to look at the swinging of a vertical bucket of water in circular motion. So let's read the question first. A teacher swings a bucket of water, total mass 5.4 kg, round a vertical circle of diameter 1.8 meter. Okay, this demands a drawing. So I'm going to draw it together with you if you're trying the question. All right, so this is a vertical circle. As I've mentioned previously, and I'll mention it again, the question will always tell you whether the circle is vertical or horizontal. Can I swing the bucket in a horizontal circle? Yes. Then that will be a totally different question. Okay, so please read. Please don't confuse between circular motion. Let's say I put a bucket here lah. Okay, maybe this is my bucket. So this bucket is going to turn this way. Don't confuse this and the one I'm about to draw, which is a vertical circular motion. They are not the same thing. One is the yo-yo one, or the loop, and then the other one is just swinging on a horizontal plane. Okay, I'm gonna just delete this. Not needed. Okay, so calculate the minimum speed of the bucket so that the water remains in the bucket at the top of the circle. Okay, many information. They say top of the circle, I follow. So let's say this is my bucket of water. Just going to draw a bucket of water here. Okay, and how do I draw the teacher's hand? Good question. I am not the artist in this channel. Okay, anyway, this is the center of circle. You don't want to draw the hand also, never mind. It's not that important. From a physics forces perspective, okay? Not that your hand is not important. Okay, so I'm going to fill this in with some water. I'm going to shade it blue. Okay, so first things first, if you don't have a diagram, draw a diagram. If you have a diagram, that's great. Determine the center of the circular motion. So this is the center of the circular motion, C. Maybe I should make this a bit bigger. Hang on. Just a bit. Okay lah, something like this lah. Okay. So my C is somewhere guesstimate here. Alright. So you imagine the teacher's hand is there lah. I cannot help you. See the good enough hand? Okay, maybe don't draw. Okay, so there's a hand there. Just pretend that it's there because I can't draw it. So we have weight of the water pulling the water down. So by right, the water should just fall out and then pour the teacher wet. Okay, so we must swing it at a certain speed so that the water remains in the bucket. The only way for the water to remain in the bucket is for us to ask the bucket to exert a normal force on the water by asking the water to exert a normal force on the bucket. Okay, I need a bit of space. Okay, so I'm going to draw things now. Normal force. So in order for the bucket or for the water to remain in the bucket, okay, the water should press up against the base of the bucket. Just like the noodle, if you've watched the noodle video, the noodle should press against the base. Alright, so the smallest thing, the boundary condition here is that normal force becomes 0. Okay, so ideally the water will press up against the bucket. So this is normal force of water on bucket. But not to be outdone, the bucket will also exert a normal force of bucket on water. And what do we care about? We only care about the water. So because we only care about the water, we only care about this force and this force. Yes, very similar to the vertical circle force diagrams that you have seen. Okay, just different scenarios. So the whole idea here is for the water to remain in the bucket, it must press against the base. As long as it's touching the base, it won't fall down. If it loses touch with the base, then it will fall down. Okay, so the press up, I'm just going to put this press up against the base. This one is so that the base press down on the water to provide centripetal force, or to help provide centripetal force. Okay, so I'm going to write an equation for net force or centripetal force on top. Net force here, which is equal to centripetal force, is equal to, take the direction of the center of the circle as positive. So here is my positive net force. So you get the positive, you get the positive, because we're all pointing in the same direction. So this will be mg plus n. I'm just going to call this n. Okay, so from here, centripetal force is equal to mg plus n. So if you turn faster, n can increase. But if you turn slower, n will have to decrease to keep the equation the same. Okay, we have explained this in the previous video. So from here, for minimum speed, okay, if let's say the past year question asks you to find the minimum speed, you just need to mention that n is equal to 0 on top of the circle. So the water loses contact with the base. N is equal to 0. So from here, what I will have is centripetal force will be equal to mg. And this centripetal force here is mv squared over r is equal to mg. We can cancel the mass of the water. So the funny thing here is it doesn't matter whether you put 2 drops of water or you put an entire gallon of water, and in fact 5.4 kg, or my dudes, it's 5 liter of water. It's like that big water you can buy from the convenience store. It's a lot of water. Okay, anyway, mass can cancel. All right, so what is left? We want to find minimum speed, v squared, or specifically v is equal to square root of, you bring the r up, r times g. We can now substitute. Now please don't make the rookie mistake of substituting the diameter. Diameter is 1.8, so radius will be 0.9. Well, miss, are you telling me for me to find the minimum speed of any horizontal circle, I just need to know the radius? Yes, and the gravitational field strength lah, but you know, we all know the good old 9.81. Hopefully we do. Okay, so I'm going to plug the values into my trusty old calculator, and this will be 2.97 meter per second. So if you travel below this speed, the water will fall out and you get wet. Okay, so I have a cool demonstration to show you. Okay, because we have Miss Ellie kind of recorded this already, so hang tight. Okay, let's look at Miss Ellie and her bucket. Teacher, physics teacher, and a bucket of water. Let's go. Bucket is empty. Whee! Bucket is full of water. Let's see if the water will fall out. Wow, Miss Ellie looks very dry. Let's try to see if she slows down. You can see the water begin to start to splash out a bit. Okay, this is what happens when the water loses contact force with the bottom of the bucket. Okay. Just gonna add more water, I guess. Because what's the fun in physics if you can't do it again? So if you're too slow, you can see, oh no. That's it for vertical circular motion. We're going to jump back to the example in the next. Thank you, Miss Ellie. You've watched Miss Ellie so committedly trying to rotate a bucket of water, okay, and you can see when she slows down, the water will fall out, okay? So here, this is part 1. So we will find that there is a minimum speed, and it's dependent on the length of Miss Ellie's arm and the size of the bucket, aka the radius of the circular motion. Okay. Second part of the question, it says, assuming that the speed remains constant, what will be the force on the teacher's hand when the bucket is at the bottom of the circle? So I'm going to assume that when they say the speed remains constant, although this question, again, is a textbook question, so it's not worded that clearly, this remains constant at the same value as part 1. Okay, that means your V is 2.97. I'm going to write it to 3SF, 3.0 meter per second. So what will be the force on the teacher's hand when the bucket is at the bottom of the circle? Okay, I guess now I have to draw a hand, right? Great. Let's draw the bucket at the bottom of the circle first. Just going to draw a nice little bucket here. Okay. And there is water. Hopefully none of it has spilled out. Okay. So the handle is here. So if you want to draw the forces on the teacher's hand, it's actually the same value as your normal contact force, because let's think about it. We assume that the bucket and the water rotates together. Is that a fair enough assumption? Can, right? Because bucket and water will spin together in its own circle ma. Okay, so let's say here, this one is the pulling force by the teacher's hand. Okay, so the force pulling by the teacher's hand on the bucket, specifically on the handle of the bucket lah, but don't have to go into technicalities. Okay, so from this is also a contact force, by the way. So if the bucket is pulling on the teacher's hand, you know what? Like after this, you can go and take a shower because it's very hot in Malaysia. And then you can fill it with water and then you start swinging lah. You will feel that this force is the highest here. And the force on your hand, okay, is actually a force that is pulling down. Newton's third law. So this first force, this up here, is the force on the bucket to keep the bucket in circular motion. This downward force here, okay, this is the force by the bucket on the teacher hand. On the hand lah. That will be this force here. Thankfully, due to Newton's third law, the magnitude is the same lah, and you just need to find one of these can already. Okay, so now we are at a juncture where we need to decide, do we want to look at the teacher's hand or will we be better off looking at the bucket? Now, as much as I love my teacher, Miss Ellie, it's easier to look at the bucket, okay? So I'm going to stare at the bucket, okay? If not, life is hard, right? So if this one is too complicated, well, never mind. I will draw, as I usually do, another one at the side for you. So this is the bucket, this is the handle. Now I don't care about the water. Okay, newsflash, this is all about the bucket. Not the water, but the bucket. Previously up here, we looked at the water. Teacher, why don't you care about the water? Because the teacher's hand that is swinging the bucket is not touching the water. Teacher's hand is touching the bucket, so I care about the bucket. Because if I can find the force on the bucket, I can find the force on the teacher's hand, Newton's third law. Okay, Lai, let's draw forces. We have the teacher pulling the bucket in this direction. I'm just going to call this F lah. FH for hand. Okay. FH. Okay, don't forget the bucket also has weight right? Bucket and water all very heavy. So this is weight of bucket. And where is the center of the circle again? If I translate the center of the circle to the side, like here, here is the center of your circle. So where's the direction of net force? Direction of net force, as usual, is pointing towards the direction of the circle. We can now bring out the net force equation. From here, I can say net force is equal to FH. Okay, we're going to take this one as positive. Direction of net force is positive, FH is positive, W is negative, minus W of the bucket. Okay, so can we actually find, because what we want to find again, we want to find force on the hand. So force on the hand will be equal to net force. Okay, don't skip. Net force is actually your centripetal force. Force on the hand minus weight. So we want to find force on the hand. Let me rearrange here. I will have centripetal force plus weight. Okay, hang on a sec. Teacher. I know centripetal force. I know. I can use mv square over r. And they say maintain same speed. So I'm going to take this 3 meter per second. Okay, maintain same speed. So if that is the case, then I can substitute 3, but W is also equal to mg. Okay, so here we have a conundrum. Previously, we don't need m because m cancels out lah. But now we need m because your force on the hand is not 0. Okay, so we're going to backtrack a bit and see if we have the mass of the bucket. Oh God, this is the total mass of water plus bucket. So obviously the weight of the bucket with the water in it will be the same as the weight of the water and the bucket, right? Okay, so this is the m that we're going to use, 5.4. I'm going to plug that in. Whoops. I show you, spoiler alert, the next question. Okay, I'm going to plug that in. 5.4 times the speed that we take. Okay, I'm going to take 3SF, 3.0 square. The radius is half the diameter, so that's 0.9 plus mass is 5.4 and G is 9.81. Oh, okay lor. We can now press Casio, our calculator. This is my calculator. 5.4 times 9 divided by 0.9. Okay, so a strange twist of fate, this is 54. Okay, that makes sense. Again, this is 5.4 times 9.81. I tend to like to separate them out in case I make a calculation error. It's easy to double check. But this is 52 point, or rather 53 lah. 53.0. Okay, so in total, 54 plus 53, this will be 107 Newton. Okay, so let's compare this force on the hand to a bucket that is not moving in a circle. If let's say my bucket is just chilling lah, you just pick up the bucket. Okay, same amount of water inside, still 5.4 kg. So we still have water in the bucket, but we're not moving in a circle. So just hold the bucket. Now if you just hold the bucket, the force on your hand is actually less, because this FH, force of the hand pulling the bucket, will be the same as mg, or the weight of the bucket. So this FH is actually only 53 Newton, mg. But when you move in a circle, even if you move at minimum speed, this force is doubled. Okay, so you will feel the strain on your hand more whenever you move in a circle. So if let's say you're doing some form of exercising and you are swinging something, you will notice that the thing that you are swinging has the largest force on your body at the lowest position. This happens if you play or if you use something like a kettlebell. Okay, so here when you hold the bucket, it's like this. Whereas if you swing the bucket, okay, I'm going to draw the bucket again. That one was hold. This is swing at velocity 3 meter per second. Okay, I'm going to scroll out a bit so you can see. So if we swing the bucket at velocity 3 meter per second, okay, in case you don't know how I swing, I'm swinging it in a vertical circle like that okay. Then this force on the hand, wow, become big. 107 Newton. Wow, no wonder Miss Ellie looked very tired. This is your FH. Okay, because the FH not only need to support W, you know, we need a net force. We need this force to be bigger because the center of the circle is here, such that there is a net force pointed in this direction. Okay, if this force is bigger than weight, then there will be a resultant force directed upwards towards the center of the circle. So whole bucket, or the force that you experience on your hand, is the weight of the bucket. Hold the bucket and swing, then the force on your hand is the weight of the bucket plus the necessary centripetal force, and this is the minimum force. This is the minimum. This is your 3, when you are here, this is your 3 meter per second. This is the minimum force. Okay, so whenever you build a system, let's say for example later in university you're asked to design, I don't know, maybe some factory system, you please consider the fact that sometimes the force experienced by your object may not be constant, especially if it's moving in a circular path. So hopefully at least that was the takeaway. All right, so in this question we look at the bucket of water and we look at the physics teacher swing it around. I will see you in the next example.